So, thin films. It has to do with, this is one of those things where a PowerPoint would be good, because you need to see pictures. So thin films, there are some that you can easily visualize. A soap bubble, and you see some colors, right? So you got light from here, it's just a whole mixture of all the colors. So you get white light, so it has red, blue, green, yellow, all the wavelengths. It's incident on a soap bubble, and then some colors you see them more pronounced, and then some colors you don't see them as pronounced. So what happens is those colors that have the right wavelength, they interact constructively, and then the colors that you don't see as well, they are interacting destructively. You also see it on a thin film such as an oil slick, right? When it rains, you get oil from the cars and so on in puddles, and you see different colors, right? And then the next one is the air wedge. Have you seen, like, you have a piece of glass on top of a piece of glass, and you kind of see some colors on there? No, maybe. Okay, yeah. Especially if you deal with like microscopes and so on, you have like a sample that you want to analyze in biology, and then you can see like different colors between the two pieces of glass. And there is a reason for that. Okay, and that's because of interference. Okay, what happens is between for example, for the oil slick, you got rays that reflect from the oil, and then rays that go through the oil that refract, and then when they get to the water layer, they reflect again. So you have a ray that traveled through this thickness of oil, and then meets the other ray that just reflected and didn't travel deeper, and then they would interact. With the soap bubble, you got soap, very thin, so it has but it still has some thickness. A ray that reflects, a wave that reflects from the soap, so it stays in air, and another one that actually goes through the soap, the second layer, and then reflects back. So it travels a distance. Let's say if the thickness is T, it goes T, back T, and then comes out again to interact with the other one that never went through. And they would interact constructively or destructively. Okay, so we'll start with the air wedge first. Okay. Let's see. Can I erase this? I don't think we need it. Okay. Okay. So we know when you have light that's incident on a surface, what happens, some of the light will refract and some of it will reflect. Okay, some light will refract and some light will reflect. So what happens when it reflects? Let's say, just to give a concrete example, let's say this is N1, it's let's say it's air, it's 1. And then let's say here is water, so N2, it's equal to 1.33, right? 1.33 for 1. And this is the perpendicular. So let's say I have a light ray coming in, and you saw last week it did some will reflect, right? Some light will reflect, and some will refract. I'm interested in the one that reflects now. So what happens to it when it reflects? What happens to the ray as it reflects? I mean, we know the angle of incidence is equal to the angle of reflection. That's for ray optics. But remember now we're dealing with a wave. So when it reflects, what happens to it? So let me just draw it at normal incidence, and then ask what happens. So almost normal, so that we can see. We can see what happens more clearly. So let's say I have it incident like this, right? Okay. It's coming in this way. Now, when it reflects, what happens is, if this index, right, if the index of refraction is in, and the index of refraction that it reflected off of from, if this one is higher than this one, when it reflects, it shifts by half a wavelength. So what happens to it is this. So instead of reflecting back like this, it will reflect back like this. So now, when it goes back, it will shift by half a wavelength. So when it reflects, so if N1 or N2 is greater than N1, it shifts by half a wavelength, right? If we're talking about angles by a pi, okay? Upon reflection, it shifts by that much. It's as if it traveled an extra distance of half a wavelength, okay? Does that make sense? It's as if it traveled an extra distance of half a wavelength. That's what happens. On the other hand, let's say we have a different one. Let's say now this is water. Let's say N2 is still water, 1.33. But let's say now here N1 is glass. Let's say it's 1.5, right? It's glass, 1.5. So what happens now? Well, you have a ray that is incident. That's not so. A ray that's incident. When it reflects, it will actually, nothing happen. It does not phase shift. It will just reflect the same way. So if N2 is less than N1, no shift. Okay, no shift. So I just need to remember that. Okay? There is no shift. Sounds good? So I need this. Also, whenever we talk about thin film interference, it has to be a thin film. If it's thick, meaning like a millimeter is thick. Like a piece of glass is thick. The distance between the two pieces of glass when they're on top of each other, that's thin. Okay? All right. So there is, the first one is going to be what's called an air wedge. And we're going to send just light of one color, of one wavelength for now. So an air wedge looks like this. So here is a piece of glass. Okay, that's a piece of glass. And then another piece of glass right below it. Right, so this is here, this is glass, let's say. And between here, this is air, this is air, this is air. So the index here and the index here are the same, but here it's just one, right? Another thing, the picture here is deceiving because I can't draw it to scale. The reason is this. This thickness of the glass is actually much larger than this gap. Okay? So this gap here, this H, this gap, we call it H, is actually much less than this thickness. Okay? But I can't draw it to scale. I have to make the glass like super thick. But we're talking about a glass of a millimeter or two, or three. But here, the distance between them, even all the way here. For H, you're talking about 1/100th of a millimeter. Right? Maybe one sheet of paper. So there is a piece of glass, they're touching here, and this end here, maybe there is a human hair. That's how thick this one. So it has to be very thick. All right, so we're trying to understand when we would have constructive interference and when we would have destructive interference. So let's look at a ray that's coming down. So here it is. I'll draw it in yellow. A ray that comes down. Of course, it will refract. I don't care about that for now. And then when it gets here, I'm curious about what happens here when it gets there. When it gets here, part of it, some of this thing, some of this light will reflect, but some of it will actually go through and then reflect from here. Okay. Some of it will come through and then reflect from there. And then some of this light will get through and then reflect from the bottom. But I'm interested in what happens between here, in this thin gap. That's what I'm interested in. I'm not interested in this thick gap or this thick gap, even though the picture says they look the same size, they're not. Okay? This gap is a lot smaller. Is my description clear? Okay. So what happens is, I'm going to call the thickness, the distance from here to here. Let's use blue for that. This distance from here to here, let's call it T. Let's call that T. So look at the green ray. The green ray just reflected from this surface. So let me ask you, the green ray, so you got the yellow ray, and then it reflects. Some of it reflects. That's the green one. Does this green one experience a phase shift or no? No. Why not? Because look at this. And 2 is less than N1, right? N1, look at this one. It's in glass, and then here is air. So this index is larger. So the index it's already in is larger than the one it reflected off. So no phase shift. Okay, so that's fine. That one is fine. Let's look at this other one. It goes down a distance t, and then goes up another distance t. Yes, it's a little angle, so it's not quite t, but it's small enough that we assume it's t. So a t down and a t up, how much extra distance did it go? 2t. Let me write delta r. Yes, it went a distance 2t, and it's in air reflected off of glass. So does it experience a phase shift here? Yeah, it's in. So now for this red one, it's in air, reflects on glass. So there is a phase shift. So it will have an additional, so it's as if it has traveled an additional half a wavelength. That's the total delta R. That's the total. Okay? Does that make sense? Yes. Okay. So now we will look for constructive interference and then destructive interference. Or destructive interference and then constructive interference. Okay? So let's look for destructive. For destructive interference, what do you need? What's the requirement? This delta phi, 2 pi delta r. Remember, this phase is not there. Delta r. For destructive, I need this to equal to 2 pi n plus a half, right? So let me write that. So for destructive, I need 2 pi over lambda times delta r is equal to m plus a half times lambda. Let's substitute things. No. Is equal to 2 pi times 2 pi, right? Times 2 pi. Did I copy it right? Can you double check if I have it right? 2 pi delta r over lambda is equal to that. I think that sounds right. Get rid of 2 pi, and we get delta r will equal to m plus a half times lambda, right? Now delta r, now we need to substitute. What is delta r in our case? Okay. 2t plus lambda over 2. Good. So I get 2t plus half lambda is equal to, spread this, or foil this. So I get m times lambda plus a half times lambda. This half lambda cancels from both sides. So I got t, we get this. T equals to m lambda over 2. Yes. So I get t is equal to m lambda over 2. Okay. Now we need to figure what lambda is. Again, what is t? That little distance. Okay. So what should m be in this case? What did we say m is? M here we said it can be these, but look at the physical picture. Could m be negative? Can the thickness be negative? No. The thickness cannot be negative, cannot be minus 1. Right? The thickness cannot be negative half lambda. So what can we say about m? What should m be? Huh? 1. 1. Can the thickness be 0? It could approach 0 the point they touch. So it can be very small. It can approach 0. So m could be 0 or 1 or 2 and so on.
Wait, is that h?
M? M is not h. No. T would be h all the way here. But all the way here, t is 0. T is this guy. You have the air wedges looking like this, right? So this part, this applies for destructive, right? Let's look at constructive. No, not destructive again. Constructive. We'll do the same thing, right? 2 pi delta r over lambda equals to what in that case? For constructive, what do we get? We will have what? 2 pi over lambda times delta r is equal to m times 2 pi, right? Cancel the 2 pi and you will have this. Delta r equals to just m lambda. Okay? This is constructive. Now what is delta r? Delta r is all that, right? 2t and then lambda over 2. So again, this 2t plus lambda over 2 is equal to m lambda. So we get this 2t will equal to m minus a half times lambda, right? Minus a half times lambda. Do we agree with that? Yeah? I'm counting on you to help me with the algebra. Okay. If that's okay, then we go on. So t, in that case, so we get t will equal to m minus a half times lambda over 2. Okay. So can m be 0 here or no?
No, because you negative.
Exactly. So what's the smallest m can be? 1. So for constructive, we need m to be 1. Right? The math said, no problem, you can plug in all the integers. The physics here says, hold on a second, we have to choose our integers. Right? Yeah. So, let me make a common denominator here, so it becomes 2m minus 1, and then the half becomes, and then it becomes 4. So 2m minus 1 times lambda over 4. And we said here m is equal to 1 or 2 or 3, and so on. All right. We'll do a couple of examples of this one. The first example we will ask is the point of contact So the first one is a conceptual. So the point of contact, is that going to be a dark spot or a bright spot? Huh? Bright? Why would you say bright? The point of contact. How far is the point of contact? What's the thickness there?
2T.
Huh?
2T.
And how big when they're in contact? How far apart are they?
Oh. Close to 0.
Okay, close to 0. Yeah. So when you get a t equal to 0, for constructive or destructive? Destructive. So it would be a dark spot. Yeah, the point of contact would actually be dark. Okay. Yeah. All right, sounds good. All right. Let me go here. Let's give an example here. This one straight out of the book. Suppose let's say this has a length L, and let's say L is 10 centimeters, and let's say here H is 0.02 millimeters. Okay, 0.02 millimeters. Let's say the wavelength, the light that's coming in, lambda is 500 nanometers. 500 nanometers. So let's find the position of the dark spots. Position of the dark spots. Let's say the distance this way is x. Here's x. And so this would be t. This one, it's t. And if I want to know horizontally what's the position of the dark spots, so let's use destructive interference, right? In this case, so dark spots, let's put here dark spots. It means destructive interference. Destructive interference, we found it. The thickness is T equals to M lambda divided by 2, right? M lambda over 2. But I want things in terms of X. So notice that T over X is equal to H over L. Do you agree with that? T divided by X is equal to H divided by L. You just think of this thing. Is equal to H divided by L. And that means T is equal to H over L times X. So let me substitute. H over L times X is equal to M times lambda. And so X is equal to M times lambda times L divided by H. Let's plug in some numbers. Yeah. So the 2 should still be here. And should still be here. Right? Yeah. Thank you. Okay, so we get X is equal to lambda is 500 nanometers. So that's 5 times 10 to the minus 7 meters. L is 10 centimeters, so that's 10 to the minus 1 meters. And then M is still here. And then 2H, so 2 times H. H is 0.02 millimeters, so that's 2 times 10 to the minus 5, right? Meters. So do all that, and you will get actually 5/4 is 1.25, right? 10 to the minus 8, 10 to the minus 5, so times 10 to the minus 3 times n. This is x. That's it. Okay. Let me convert this. By the way, this here, what units would it have? This number here. It should have meters, right? Because n is a dimensionless number. It's just an integer. It's like, in this case, 0, 1, 2, 3. So let me change this to millimeters. So it's going to be 1.25 millimeters times n. That's x. So you will have this. So basically, here's your air wedge. You would have a dark spot here. You would have a dark spot here. And then you have a dark spot here. You have a dark spot here. And they're spaced by 1.25 millimeters. That's their spacing. So when you look at the two pieces of glass from the top, you will see dark, bright, dark, bright, dark, bright. Okay. The separation, the distance between two adjacent bright spots. For example, let's say the first two adjacent dark spots. The first dark spot is at 0, right? So at x equal to 0. And then the second dark spot is at when n is equal to 1. So that distance would be 1.25, and so on. Does that make sense? Okay. I'm going to erase this other board so we can do the next example. Also has to do with this. This next one, suppose we have an air wedge formed by two pieces of glass and then a human hair at the end. Okay, so this, here's one. And then here is the second piece of glass, and then there is a human hair. Okay, I'm magnifying it. There is a human hair. So as you expect, that's not going to be very thick, right? It's going to be, you will have some height or some thickness each. So as you look through, you shine light of lambda equals to 771 nanometers, that's lambda. And so when you shine light of 771 nanometers, and then you look at it, you look at the two pieces of glass as you look from the top, and you count, here's one bright spot, two bright spots, three bright spots. You're really patient. You end up counting 179 bright spots. Okay, yeah, you count 179 bright spots. And the question is, how thick is this human hair? If there are 179 bright spots. So if, let me write it here. If there are 179 bright spots, how thick is the hair? In other words, find H. What can we say? How are we going to do this? Where is the first bright spot? Let's say m equals 1, yeah. So here's, it's going to be dark here, right? And then there would be some bright spot here. Right, so there'll be a bright spot here. And then there will be another bright spot here, right? And then there is another bright spot here. And then all the way when you get to here, you get your 179. All the way at the end. Either at the very end or the one adjacent to the very end. So that doesn't change much. So what's the thickness? So what do we do? Bright spots, therefore, constructive or destructive? Constructive. So what's the equation for constructive? Over there, right? Down. You got what? T, the thickness is 2m minus 1 divided by 4 times lambda, right? What should we use for m? Where is the 179th bright spot? Toward where they meet or toward all the way there? Yeah, toward the right. Okay. And toward the right, what's the gap? H. So T is equal to H at the 179th bright spot. So M is equal to 179. The first bright spot is at M equal to 1. The second one is at M equal to 2. And so on. So 179 is M. Okay. So that means this. H will equal twice 179 minus 1 over 4 times lambda. And lambda is 771 times 10 to the minus 9. Or 7.71 times 10 to the minus 7 meters. Yeah.
So could we use the dark spot one, but use 178 instead?
You're gonna be about the same, yeah. Yeah. Yes. Yep. Definitely. Because they alternate. Yeah. And so you will get H, so you plug in the numbers and you get H to be. I'll just look at the answer. What's the answer? It says 6.88 times 10 to the minus 5. And that's 68.8 times 10 to the minus 6. And that's now 68.8 micrometers. About 68.8 micrometers. And yeah, a typical human hair is about, depends, so 70 micrometers, okay, about. Okay, any questions on this? The next one is, it's called Newton's rings. It's similar to the air wedge, but let's say, instead of having an air wedge, this one is qualitative. So Newton's rings. Let's say instead of having an air wedge like this, let's say I have, the glass is bent. So here's glass, and this one is another piece of glass. but let's say it looks like this. It could be a bowl, like three-dimensional object. Just like the piece of glass there, it's not like two-dimensional. What would you get here? Dark or bright?
Dark.
Yeah, it would be dark. That's the point of contact. And then you will have a bright spot, right? Let's say the bright spots are red. If you get bright on either side, and then you get dark. So, does that make sense? Okay. Now here's the conceptual question. Do you think? By the way, if you look at it from the top, if this is a bowl, if you look at it from the top, you will see the following. Like a top view. Like a top view. Imagine it's a bowl of glass like this, and then there is glass below it. And this is exaggerated. The gap here should not be that big. Okay. You will see a dark spot here. And then what would you see here?
Ring.
You see a ring, yeah, Newton's rings, right? And then you would see a dark spot, like a dark ring, right? And then you would see a bright ring. My question is this: will the spacing between the rings get larger, or will it get smaller, or maybe it will just stay the same? Over there, the spacing was even, right? They were evenly spaced because it was linear. What do you think? Look at X over there. X is equal to m lambda divided by h, right? Divided by h. And h is like the height, right? So what's happening to that height? The gap.
It's increasing.
The gap is getting bigger. So what happens?
The gaps between the spots get smaller.
Yeah, they should get squeezed together actually. Because h here, L is fixed. L is a fixed number. So h here is getting larger because it's not just going linear like this. You're increasing the gap more and more. So the spacing. There are nice pictures in the book, so look at them. In the chapter. Let me see. Yeah, they have nice pictures on there. Let's see. There are soap bubbles also. And then let me discuss maybe the soap bubble for a moment, and then just try to understand how that works also. Very similar to this, very similar to this one. And so let's see how it goes. A soap bubble